Welcome back to our channel. In the last video, we used the first principle to differentiate functions like x squared, x cubed, and 1 on x. That worked, but it was too long. So today, I'm going to show you a much faster rule that covers powers of x in one step. It's called the power rule. So by the end of this video, you'll be able to differentiate x to the power n for positive, negative, fractional exponents, and you know the domain condition to watch for. So first of all, what does the power rule says? The derivative with respect to x, the derivative with respect to x of x to the power n is n times x to the power n minus 1. So it's a very simple rule. Derivative of x to the power n is equal to n times x to the power n minus 1. So what can we note for? We know that this works for n elements of real numbers. And what are real numbers? A real number can be a negative whole number, it can be a negative, it can be a positive whole number, it can be a fraction, yes, it can even be a decimal, but all of these are real numbers. So this method or this power rule works for all real numbers. So I'm going to summarize all of this into 3 micro procedures that you need to follow up. So I'm going to write it down. Procedure for z on zx of x to the power n. So what's the first procedure you need to follow up? You bring the exponent down as a multiplier. Bring the exponents down as a multiplier. This can be seen as n was brought down here as a multiplier. The next step is subtract 1 from the exponent. This can be seen as negative 1 here was added to n, or 1 was subtracted from n in this initial formula. The third step is state domain if it matters. In this case above, the domain n belonging to real numbers was stated, because if the domain is not stated, the whole power rule does not more make sense. Yes, because it becomes unbounded. That means it does not define the type of values of n for which our function works. But with a domain stated, we know the different values of n, or the different values of x, or the different values of each term for which our procedure or our formula still works. So in order to tackle this, we are going to work on 3 main examples. I'm going to tackle the first example, and the next examples will be more like practical questions where you guys have to work on it, then we solve it together. So I'm going to start with example 1. Example 1. Positive integers. Positive integer powers. So we'll write down our question. Differentiate f of x equal x to the power 5. So I will do this slowly and perfectly. So what's the first step we have to identify here? We have to identify our power. What is our power? In this case, our power is 5. And what does our power rule state? It states that the differential of x to the power n is the same thing as n times x to the power n minus 1. So the differential of x to the power 5, which is d on the x of x to the power 5, is the same thing as 5 times x to the power 5 minus 1, which is 5x to the power 4. So what do we know? First of all, we have already done our first step, which was bring the exponent down as a multiplier. Our second step was subtract 1 from the exponent. And our third step now is to state the domain. X to the power 5 is defined for all real x. And 5x4 is also defined for all real x. What does that tell us? That tells us that the derivative is valid for all real values of x. So we can then conclude that the derivative of x to the power 5 is equal to 5x to the power 4 for all real values of x. And that is our solution to this question. What can we observe? Compared to the first principle of derivation, which had to go through limits, it took us several steps to solve a question similar to this. But using our power rule, we were able to come up with the answer in how many steps is this? One step. One step to come up with an answer compared to the first principle of derivation. So we're going to move on to the next question. Practice question 1. Let's write down the question. Differentiate g of x equals to x to the power negative 2. So I'm going to leave you guys time to solve this question. If you have any remarks or your different answers, you post them in the comment section, and each and every one of us are going to get back to you. We'll make our comments and observations. Okay, so I'm going to start solving the question, considering that each and every one of you guys have already had time to tackle this question and come up with your various answers. So we're going to follow the same rule. What was our first step? Bring the exponent down to the multiplier. What does that tell us? D on the x of x to the negative 2 is the same thing as bring our exponent down to the multiplier. Our first step. What does our second step tell us? Subtract 1 from the exponent. What does that mean? Minus 2, we subtract 1. What does this give us? Negative 2x to the negative 3. Our third step is state the domain if it matters. In this case, our domain is for every real values of x. For every real values of x. That is what our domain tells us. So what can we conclude then? Therefore, the derivative of x to the power negative 2 is same as negative 2x to the power negative 3 for every x element of real numbers. So what can we observe? We were able to come out with the solution in just one step, the same as the first method. So if you observe very well, in our first question, we had positive integer powers, and it worked. In our next question, we had negative integer powers. Negative integer power. And it still worked very well. So we're going to move on to our second practice question, which is our third question. Practice question 2. We are going to work with fractional powers. So what does the question say in this case? Differentiate h of x equal to x to the power half. So if you observe very well, this is the same thing as square root of x, and our power in this case is fractional. So we are going to follow the same methods which we use, or which we applied in the first two questions. What do we say our first step is? Our first step is to bring down our power as a multiplier. What does that tell us? Differential of x to the power half. We bring down our power here as a multiplier. What is our next step? We subtract 1 from our power. And what does this give us? Half x to the negative half. What is our third step? We specify the domain for which this function works. And what does this work on? It works for every real value of x. So what can we then conclude? We can then conclude that the differential of x to the power half, which is the differential of the square root of x, is equal to half x to the negative half, and this is valid for all x elements of real numbers. So what did we observe? We observed that our power rule worked for positive whole numbers or positive integers. It worked for negative integers, and it has worked for fractional powers. So we can then conclude that, or we have observed, because it was well stated in our definition, that this power rule works for all real numbers. So we have observed that it has worked for our first case, which was a positive power x to the power 5. Our next case was a negative integer, negative 2, and our third case, which was a fractional power, and it has worked all the times. So thank you very much for following up this video. In the next video, we are going to tackle the derivative of constants. Yes, so the video is going to be linked up on this video. So hoping you guys meet us in the video. Bye.